All right. Yeah. Hello, everybody. Let's get started. Just a quick reminder, now that both groups did lab this week, the Monday group lab report is due next Monday by 5 p.m. So only those of you that were in lab on Monday will have that lab report due. So I think there were 6 of you that did the lab on Monday. So Brittany, we have 6 only assigned for the lab report on next Monday. And then all of you that did lab today, your lab report will be due next Wednesday at 5 p.m. And then you'll have that also assigned to you. Starting next week, we had 3 volunteers moving to Monday lab. So as of next Monday, we will have 10 people on Monday and 12 on Wednesday. So we have good distribution of students. So that's great. We finished nutrition labeling last Monday, and we started data analysis, but I just want to have a little bit of a recap before moving on with where we were. So is nutritional labeling required for all food? No, Ash. No, Kevin. Why not?
Certain foods like produce and whatever that not been adulterated, I guess.
Or processed, or any other ingredients added to it. Shelled eggs, for example.
The other one is when there is a larger package of packages.
Yes, a big package within it, individual packages, you will find nutrition label on the outside box or package. Yes, okay, so what agencies regulate nutrition labeling? We have 2 federal agencies. One was, Sam?
FDA.
FDA is one, and there is another one. Yes, Stella. Yeah, okay. I got the letters confused. Say that again. FSIS, Food Safety and Inspection Services. They particularly regulate meat, poultry, and eggs. Okay. What type of analytical methods are required to obtain the values listed on the nutrition label? So this is a very common method that question that I would ask in a quiz or exam. When I say what type, category, or title of methods, not a particular method. I'm not asking for a particular analytical method. I'm not asking you to tell me Caldol for protein or whatever. The title or the type of methods that are required, that a company is required to follow. Methods that are official methods of analysis. Okay, So official methods of analysis, these are methods that have been verified and approved by regulatory agencies. Okay, so like AOAC or AOCS or cereal and grains, and several others that would approve and validate methods. They are known as official. They are also known as reference methods. They are also known as primary methods of analysis. So that's when I say what type of analytical, you would want to think, am I looking for official methods? Am I looking for secondary methods of analysis? Or am I looking for, official, primary, reference? They all mean the same. What are new changes in the nutrition label? What can you think of, Sally?
The calories is,
Bold.
larger quantity.
It's screaming at you, number of calories. What else, Taylor?
Added sugars.
Added sugars, yes. What else?
I'm not gonna do that.
Say your name again.
Yes, potassium.
Potassium, yes. In terms of vitamins, do you remember, Carol?
Vitamin D.
Vitamin D,
And vitamin C is one of those.
A and C they were removed and vitamin D was added, yes. Anything else? Ash?
I was going to say the stuff that, I said about vitamins, but, calories from fats.
Yeah, it was removed, yes. Very good. Was there anything else, Carol? No. All right, I think we got it all. When can you claim calorie free? Yeah,
You have less than 5 calories per serving.
yes, when you have less than 5 calories per serving, you can call it calorie free. Is the label in compliance when an added nutrient level is 80% of what is listed? Why not, Priyansh?
For an added nutrient, it has to be 100%. If it's naturally present, we can.
Yes. For added nutrients, at least 100%, it's okay if it's a little over. For nutrients that are already endogenous or native to the product, 80% at least or higher, but there are few components that we don't want them to be over 120%. What are they?
Calories, sugar,
Yes, the salt, the bad stuff, the excess of is not healthy. Fat, salt, sugars, and then total calories. Yeah. Cholesterol as well is one of those. Perfect. So these kind of questions you might see on a quiz. So try to, study and try to look at your recap questions and see if you're able to answer them. It's good for study guide, kind of. Okay. But definitely these are not the only things you need to know. It's just an example of what you might see. We started on this. We talked about all of these different measurements, measures of central tendency, reliability, and then the fitting curve for prediction of concentrations. Mostly we will use that. And also how we report results. So I will talk about each one of those in more detail. And what I want you to do for extra credit of +2, pick up a piece of paper and start solving some of the questions I'll be asking in class, and I'll give you time to work on them. And at the end, take a picture of your piece of paper for your reference and then hand it over for your extra credit. Okay, but take a picture so that you have answers for those questions. Okay, so calculating the mean and determining the median for these set of data points for percent moisture. So take a moment, and when you have a value or an answer, raise your hand. This is, of course, you know how to do this. It's just practice. You'll be doing a lot of that. Make sure you write your name on that piece of paper. Okay, ready, Isaac? What's your average?
For an average, I have 82.5.
Correct? Yes?
The median 82.63.
Yes. So just make sure on the piece of paper that you write how you got to this answer. Okay? Okay. You've seen this somewhere in your past, I'm sure of it. But let's try to remember again. We talked a little bit about precision and accuracy last time. And when you look at the dots represent data points. And then when you look at A, does this tell you good precision, bad precision, good accuracy, bad accuracy? What does this remind you of? Those data, the dots are data points for a particular assay. Is this good precision or bad precision? Go ahead, remind me of your name.
Medora.
Medora.
Good precision is bad.
Okay, good precision because data points are close to each other. So for whatever reason, you're being very precise and the method is giving you precise data. But for whatever other reason, it's not accurate at all. Okay, so what about B? Go ahead. That's it.
Good precision and accuracy.
Yes, so we're having data points clustered in the middle, so that's kind of the bullseye here. And so close to the true value, and then the data points are close to each other. So that's a perfect example of good precision and good accuracy. What about C? Go ahead. Sarah. Sarah, okay. Yes, this is whatever you're doing is wrong. It's not giving you good data, or not you perhaps, the method itself. It's not reliable, not giving good precision, not good accuracy. What about D? They are floating around the center. So if you take the average of these very scattered data points, you might land somewhere near the true value. So here you are having potentially good accuracy, but really very poor precision. You have multiple replications, precision is really bad, but it's really giving you an average close to the true value. We definitely want to be in the area where you have good precision with accuracy, which is good. Any question for me? Okay. All right, so in terms of accuracy and how we measure it, we obtain our average based on a set of replications, and then we either have a reference sample that we are measuring alongside our samples, or we have a reported value, or somebody gave me the data points for a reference value. Let's say I have a starch kit, an enzyme kit to determine total starch. They send with the kit a standard starch sample, and you have your samples that you want to determine total starch in. You run your samples, you run the standard starch, and then to determine the accuracy of your procedure, you look at the value you got for the standard starch, and in the pamphlet that they gave you with the kit, they tell you what's the percent starch in your reference. So you have an average value and you have a true value, or a reference value, or a published value. So later on, when you are assigned a food product and you determine fat, protein, ash, moisture, there is a USDA website that tells you what the different component or composition is for that particular sample. So you use that USDA value as your true value. So there's always a true value that you can get hold of, and there's the X with the bar on top, that's the average that you actually generate when analyzing the data. So there's the absolute value and there's the relative value. The absolute is basically just the difference in absolute term. So you don't report it as negative value or anything, it's just in absolute term, the difference between your actual measurement and the true value. There is the relative error, so it's relative, the difference relative to the true value. So the difference relative to the true value. And usually to assess accuracy, we calculate percent relative error. So basically the relative error multiplied by 100, that gives you a percentage of relative error. Anything less than 10% you consider good, less than 5% we consider excellent. Excellent accuracy, good accuracy, or maybe terrible accuracy. Above 25% of relative error, just not. So it's kind of a rule of thumb. Anything less than 5% is excellent, less than 10% is okay, is good, is acceptable. And anything really high, above 25, it would be miserable and bad, and there's something that you need to do. Okay, so you are using a mechanical pipette, and you're trying to determine the accuracy of that mechanical pipette and determine whether or not it requires calibration. Because in a lab, in a research lab, you want to make sure that your pipettes are calibrated so that you are, getting accurate measurements. So what you do to test it before we send it to the calibration folks, to the maintenance folks to calibrate it, we measure out what we think is 1 ml and we weigh it. Okay. And then we get different readings, and if its water density is close to 1, so we're going to assume that the grams are equal to milliliters with a little bit of decimal difference. Okay, so calculate the mean. And what would be your true value in this example? 1. Yes, 1. So we calculate the mean, we have the true value, calculate relative or absolute error, relative error, and percent relative. Okay. Okay, Sarah, you have answers?
Oh, yeah,
Okay, go for it.
for the mean, I got there point nine nine six for the later,
Yes,
should really we're using this one.
yep,
Absolute and the relative is the same, and you're.
yes,
100%, 0.39.
very good. All right, so these are the values. Make sure on your piece of paper you show how you got to these values. So the way we do that, like I said, is we weigh and we convert to volume, and that's what you're going to be doing in the lab. You're going to be using different measuring tools and volume measuring tools, and you are going to be weighing and converting to volume using the density of the water. And then you would get the calculated mean in milliliter, excuse me, for that unit. Don't forget use the unit in your own sheet. And then the difference, although it's a negative value, you just reported an absolute value. And percent, and then relative, it's the same because it's divided by 1, so it's a same number. And then the percentage, you multiply this by 100 basically, and then you get 0.39%. Very, very accurate, high accuracy. We don't need calibration. Your mechanical pipette is good to go. So in terms of precision, the first thing we calculate is standard deviation. So the deviation from the mean, basically, and this equation is, you want to remember, it's very easy to remember. It's the square root of the sum of the difference of each measurement and the mean. So this is the mean, this is each individual measurement. So the difference and then square, and this is the summation. So each of the, if you have 3 different measurements, you'll get 3 different values to add up. And they're all divided by n minus 1, which is the total replication minus 1. So if your application is 3, then n minus 1 would be 2. So you will get standard deviation. In the lab, you will be asked to report coefficient of variation. And I'll give you an example why coefficient of variation is important. So the coefficient of variation is taking into account the size of the mean. So basically, coefficient of variation, also known as a relative standard deviation, it's relative to the mean. It takes into perspective the size of the mean, and then you multiply by 100, gives you a percentage. Again, rule of thumb here, anything less than 5% is excellent precision. Between 5 and 10, I would say good, acceptable, you're okay, you don't need to repeat. Anything above 10, depending on the assay, sometimes I go, well, if it's 12%, that's okay, that's enough. Sometimes if it's 25, 30, 40%, something is really, really off, I would ask you either to eliminate the replication or perhaps to redo your analysis. So If you don't have precise data, you can't really trust the data. So the precision is often evaluated by coefficient of variation more so than standard deviation. I'm going to illustrate. So near infrared instrument, we learn about it later on during under spectroscopy section of the class. But in NIR, you can do quick measurements of composition. You calibrate the unit using primary methods of analysis, and then you can put your powdered sample directly in the instrument and get a measurement within seconds. So if I'm using the NIR and I'm running a lot of different samples on it, I'm running a flour sample, like wheat flour sample, and I'm running at the same time protein ingredient samples, like soybean. I'm just running different samples at different days, okay? Not necessarily at the same day, but I also am validating using an official method of analysis. So I'm running the soy protein isolate using 2 mass. So flour in general has anywhere between 9 to 15% protein, wheat flour. Soy has protein isolate is really above 90% protein, so it's really high protein. So the measurement is really different between anywhere between 10 or 9 to 15 or 9 to 9 to 9. Okay, I measured by NIR and I got 12%, and I calculated standard deviation, and it was 1.2. Here, I ran my protein isolate on 2 mass, which is a nitrogen analyzer based on nitrogen combustion, and it is an efficient method of analysis. We will learn about it in the protein chapter. And I got 92% plus or minus 2.76 standard. Which of these 2 methods are more precise? Can you tell? Go ahead.
The first one.
Okay, so yeah.
The first one would be more precise than the lower standard deviation, even though it's not accurate, it's only a 12%.
This is one answer. Any answer is a good answer, but is it the correct answer? Who wants to either agree? Let's take votes. Who think that flour sample measured by NIR, the NIR method has better precision than the 2 mass method? If you think like Raven, this is more precise, raise your hand. Okay, raise my up so I can see. Good. Hands down. Who thinks the opposite? No one. Not even one. For a +3. You're almost ready for the +3, huh? It's the other way around. This is not more precise than this. Why? Because if I want to calculate coefficient of variation, I'll take the standard deviation, I'm going to divide it by my mean. I'll take the 2.76, this is about 10%. If I take 2.76 divided by 92, I don't know, how much is that? This is about 3%. So which is more precise? The second one is more precise. So this is the exact illustration why coefficient of variation is what we will be using the entire semester to evaluate precision, because you're going to be working with different samples of different measurement size, different protein concentrations, different fat concentration. How am I going to compare the precision of the methods when I have different samples I'm analyzing? The coefficient of variation corrects for the size of the mean. Remember those terms. Coefficient of variation corrects for the size of the mean, because again, you want to look back here and say, I'm dividing by this mean. So I'm taking into account the size of the mean, and then I multiply by 100. So in your lab report, you'll see that we almost always ask you to calculate coefficient of variation to determine precision, not accuracy. So how precise is your value, not how accurate is your value. How precise is your value? We need the coefficient of variation. So in this particular case, it kind of visually seems tricking you that this is more precise than this. But when I correct for the size of the mean, this has 3% coefficient of variation, less than 5%, excellent. This has 10%, is okay, not that impressive. Okay, another thing we use for precision, we don't use it very often. You will learn how to use it next week in lab, is the confidence of interval. How much confidence we have in our mean, that the mean lies close to the actual, or what's the range that we think our mean is that is close to the true mean. So how confident we are with the representation of our average. So basically, the confidence interval is the average plus or minus standard error. So we will have the t-value multiplied by standard deviation over square root of n, which is the number of replications. So when you have number of replications less than 25, we use the t-table. I will show you in the book where you find it. If you have replications greater than 25, number of reps, you use a table of z-values. So on page 49, there is table number 4.3. It gives you values for t, for various levels of probability. 95% confidence is very common percent confidence we use, or 90% or 99%. In our world, in food analysis world, we often use 95% level of confidence, that we are 95% sure that our mean lies within the specific range. The narrower the range, the better is our confidence in our data and in our precision of the data. The narrower the range, the more precise we are. Okay, so let's take the same example where you have the mean, and instead here of calculating accuracy, 5% relative error, you're going to go after standard deviation, coefficient of variation, and the confidence interval. And since we have 3 reps, I read the table, I look at degrees of freedom, which is n minus 1. For 3, it will be 2. If I want a level of confidence of 95%, then my t-value is 4.3. You will need to know this going into lab next week. Actually, Brittany is going to guide you through this, where you're going to find the t-value in order that you can determine the confidence interval using the Excel. So where to get the t-value and which equation you will use to get confidence interval with 95% confidence. It's really good that you are working on practicing these because all of next week's lab is about measurements and calculations and understanding the accuracy and precision of your data. Anybody with values to share? Do you have values, Kevin? Go ahead.
Mean is the same as the previous problem.
Yes.
So 0.9961.
Okay.
And standard deviation, I had didn't scientific, so I did 1.93 times 10 to the negative third.
Okay. Yes.
Then CV is 0.19%,
Yes.
and then CI. So you want to report it as the mean plus or minus the percent of it. So then it's the same mean 0.9961 plus or minus 0.0048%.
Perfect. You got it. Okay. So standard deviation is either 1.93 times 10 to the negative 3. That's correct, Kevin, or 0.0019 rounding. And then the coefficient of variation divided by the mean, but which mean did you divide it by? This one, right?
Yeah.
This. So due to rounding, it seemed like as if we divided by 1, but you really want to divide by the actual mean, not by the true mean. So you divide by the actual mean, and since it's very close to 1, you get with rounding 0.19%, which is excellent precision. And your confidence interval with 95% confidence is the average lies within a confidence of plus or minus the mean plus or minus 0.0048. So your interval is this, the absolute value of 0.0048. That's your absolute confidence interval. And then you would report your mean plus or minus that. Okay. Any questions about any of this? This is, you know this probably from high school, and a little bit from your undergrad stats, but I wanted you to remember this because you will be using it a lot. Yes, no?
Yeah. What's the X under the percentage distribution?
For the coefficient of variation.
Yeah.
So that's the average. So X with the bar on top, that's your mean. That is this. Yeah. Yes. Good question. Guys, let's pay attention a little bit to the questions. They might be relevant to your questions. So the XI is any of the replication values. So rep 1 value, rep 2 value, huh? Yeah, but make sure you include them all when you're doing the summation. Okay, let me go to the actual numbers. So this is your actual mean. So your standard deviation is equal the square root of the first one is your first measurement. Let's say 0.9940 minus your mean 0.0, no, 0.9961 squared plus, because it is the summation, right? Plus the other one. The other value is 0.9978. 9978, again, minus the mean squared. And that continues to the last replication. And then over your n value.
And minus one.
Yeah, oh, yes, thank you. And this is all squared, 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 and then n minus one, and then you get that. Okay? You've all got the values here. Moving on. I'll hold off to recap for next lecture and sources of errors. So in lab next week, we will be talking about sources of errors that will potentially lead to poor precision, poor accuracy, and we're going to talk about why you might have poor precision or poor accuracy. There are different types of errors, and there's also a question for lab report for next week that asks you about the different types of errors that you have encountered while running the experiment. Did you have any systematic error? Like, did you work with a pipette that hasn't been calibrated? Instead of pipetting 1 ml, you are always pipetting 0.9 ml consistently. So you're really getting good, very precise data, but not close to the true mean. It's more than 10% away or 10% or larger away from the true mean when the pipette needs calibration. And not only pipette needs calibration, sometimes the balance needs calibration. So the balance is always consistently giving you a specific weight, but it's wrong weight. It needs to be calibrated. So when an instrument or a tool needs calibration, that's systematic error. It's not your fault, it's a system error fault. You're always getting very precise data, but very inaccurate data. Random error can be really anything. Random error, sometimes we call something called experimenter error. You are the experimenter. You have a particular set of experience that is different from the friend next to you. So you have different random errors associated with how you run the experiment compared to your friend. So you always have something we call experimental error. Random error due to the experiment. Another random error that we can avoid, and we will always warn you about this in lab. Let's say you are doing fat measurement. You are weighing a flask with the fat that you have extracted from a food product. You weigh the flask on one balance. You went and did the extraction and collected the fat in that beaker, flask, or tin, whatever it is, and you brought it back to a different balance and weighed it. So there are two different balances. They have different vibrations, they have different precision. So you might get an error because you didn't go back to the same balance you've used originally. So that's a random error, and that's going to increase your decrease your precision and decrease your accuracy. But we call this random, but we learn in lab and we try to tell you avoid doing such avoidable errors. Use the same balance, the same set of tools while you're running the same experiment. Okay, blunders. We are all prone to blunders, especially on a Monday morning. I do blunders, TAs run into blunders, and of course, you guys coming sleepy after a very fun weekend. So you come to the lab, you're really tired, prone to errors. So what you do, we tell you, you have two different reagents, HCl and NOH next to each other, and you are determining titratable acidity. So you have juice or a 7-Up or whatever we give you to determine total acidity. In the burette, you have to have the base. You have to have the NaOH in there to titrate the acid to determine percent acidity. So instead of putting NaOH in your burette, you grab the HCl and you keep titrating, and no change in color. So that's a blunder. Another blunder that one of our beautiful, wonderful TAs done one time is prepare a 1% NaOH solution instead of a 0.1% NaOH solution. So we are titrating with a highly concentrated NaOH messes up our experiment. So blunders, we are all prone to them and we might encounter them in the lab. All right, just a quick recap of the difference between specificity, sensitivity, and detection limit. I talked about it last time, but let's see how much you remember. The following implies sensitivity. Detection of only one constituent has a very low threshold. Detection of minor change in constituents, compound answer, all of the above never. Sam, cool, quick, go ahead.
A and C.
A and C. You reminded me of Harvey, the game, the Family Feud game. So they hit and then they think. And they raise your hand and then you thought about it. What did you say?
A and C.
A and C. These two. Okay, any other answers? Carol?
B and C.
B and C. Okay, hold that thought. I said, you know, simplicity in life. It's always good. C is your answer. So, yes, sensitivity is basically detecting very, very small difference between a couple of samples. So the more sensitive the method, the more it is going to detect a very small difference between two samples. The first one, A, is detection of only one constituent. This has to do with specificity, how specific your assay is. The very low threshold has to do with detection limit. How low can we go in detecting and being confident in our analyses? How low of a concentration we can detect and measure? I have 2 minutes. Standard curve. We will be plotting a lot of standard curves. The first one we're going to plot is basically during our caffeine HPLC lab. So what we do is we have our samples that we don't know. You're going to have tea, coffee, energy drink, some other drinks where we're going to determine caffeine concentration. So we really want to know our concentration in unknown samples using a standard curve. In order to do that, we need to have standards. So we will have caffeine standards and we will prepare known concentrations for each of our standards, 4 to 5 different concentrations. And then we're going to measure absorption of caffeine using HPLC, using a UV detector. And we're going to measure the area under the curve of that particular caffeine peak based on the absorption. And that would be our dependent variable that we will be measuring. And our independent variable is the concentration of the unknown of the standard. And then we plot the equation of the line, linear regression, and then we predict X based on the absorption. So Y equal AX plus B. We will have a standard curve, we have the intercept, we have the slope, we measure the absorption, which is Y, we back calculate X. So we want to make sure that, so the independent variable is the X-axis where we have the concentration of the standard. The dependent variable is sometimes the absorption measurement or area under the curve measurement. And then we construct the curve And we can get coefficient correlation, which is only the R. That means how well the data fit a straight line. And then, but what we really care for is the R squared, which is the coefficient of determination, how the power of prediction basically, or how much measure is of the measurement is explained by the regression. Basically, how well the prediction is. So the higher the R squared, the closer it is the one, the better prediction and better confidence we have in determining the unknown concentration. And here's an example, that's the last thing. Here's the example that we usually run a standard curve for determining protein content in solution. We use bovine serum albumin, which is a protein, as a standard. We prepare different concentrations. We measure absorption at a particular wavelength. We plot the point. We get the equation of the line. We have our R squared figure. Then we run a sample of unknown protein concentration. We have the absorbance. We calculate X. So this is basically how we utilize standard curve, and we're going to do a lot of that in lab. On Friday, I'll talk about significant figures. Thank you, guys.
Professor?